Okay, short class today. Just want to do a couple of slides, general overview on the state of fabrication technology and in the integration of components, and then we look at transmission gate. All right, so I'm assuming you have heard of Moore's law sometime. Moore's law was more of a prediction and an observation by Gordon Moore. He was one of the founders of Intel. Okay, there were three founders for Intel. He was one of them. Robert Noyce was the other one, which has now ordered the name to our School of Computing. So the Noyce School of Computing at Cal Poly is named after Robert Noyce. All right, so Gordon Moore predicted. Moore predicted that the number of transistors that were integrated on one single piece of silicon would double roughly every 24 months. That prediction and that observation has held true over the last few decades. So going on close to 50 years now, all the way from 1970 to 2020, and even the 5 years since 2020, that prediction is still holding true. Okay, even though we are now approaching the physical limits of what we can do with the current fabrication technology. So there are some variations every year here and there, but for the most part, it's still a linear. It has been a linear relationship. So when they first started integration, that's where the name came from, right? You had all these separate components. We create them. We create a circuit on a breadboard and mount them on a PCB. We had discrete transistors, resistors, diodes, etc. And then they came up with an integrated IC fabrication technology, meaning you are integrating all of these components and making them or fabricating or manufacturing them all at the same time on one single piece of silicon. Okay, hence the name integration, integrated circuit IC, and also the name where Intel comes from, integrated electronics. That's where the name for Intel comes from, right? So in the early stages of integration, they didn't, I guess, the scale obviously was not something that they could predict, right? No one could predict 50 years ago how far we would come with this integration technology. And so when they first started, they just call it small scale integration. I believe at the beginning, it was not even called small scale. Small scale would have been something that would come with hindsight, right? So 5 years, 10 years, 15 years down the line, they made advances in fabrication technology and integration technology. That's when they decided to name the earliest steps or the earliest ICs as small scale integration. So for about roughly 10 years or so, those years are referred to as small scale integration. The number of transistors on a piece of silicon or one single IC were limited to a few thousand. Okay, and then came medium scale integration, where you could now increase the number of transistors on a similar size microchip, and you could come up with complex circuits like multiplexers, counters, several logic gates to implement logical functions. Then after that came large-scale integration, which were the earliest microprocessors. And then came what is currently known as VLSI, very large-scale integration. So after large-scale integration, they kind of ran out of superlatives. They added very and ultra, and now I'm guessing mega and giga or whatever. But VLSI is still in vogue, right? VLSI design, VLSI fabrication technology, that's where it comes from. It stands for very large-scale integration. It simply refers to the number of transistors that are there on one single integrated chip. The early microprocessors, by the way, when I was a student, we learned assembly language programming on 8085. My senior project was based on the 8086 microprocessor. We created a telephone line measurement device using the 8086 microprocessor. Assembly language programming. I don't know if you all still learn assembly language, right? So I did too at that time. Okay, those devices are still available today. We use them in the lab. They're still used for many applications, right? small single application systems do not need large microprocessors. We do not need, I was going to say, we do not need like powerful processors in mobile devices, but that's not true nowadays. We have powerful computing at our fingertips in our pockets at all times. But let's say we take, take an appliance, for instance, or a small system that requires like a microcontroller or even a small microprocessor. Not need many powerful components for that. If it's a single application device or single application system, we might simply need like a counter or like a demultiplexer or something like that. And so these devices are still available today. Just a random search that was performed on the DigiKey website a couple of years ago yielded about 15,000 different items for gates, inverters, thousands of counters, decoders, multiplexers. All of these are still in existence and in use today. And this is the reason why we still study those. Okay. So even though it might seem, okay, this is something that was created like 50, 60, 70 years ago, the reason we still study them is because they are still used today. So as an engineer, you might end up working for a company or a startup that you might still use these devices. Same logic applies to discrete transistors, right? We worked with discrete BJTs, MOSFETs, about like six MOS devices on one chip. That's a very, very low level of integration, right? The same size of the chip could probably handle like hundreds of thousands of transistors. We had only like 6 on those. There is a purpose to those, right? Right now, students use them to learn, but there's also real life applications where you can use them for a specific application. So there is a purpose to why we study them. All right, analog transmission gate. If we have a MOSFET device, we talked about using MOSFET devices as digital switches. So digital switch would be operating in cutoff or saturation, either on or fully off, either fully off or fully on, right? We could also use it as a switch in the triode region. In the triode region, the device is on, but the voltage and current have a linear relationship. If they have a linear relationship, it is a resistor. The device, can be modeled as a voltage controlled resistor. In fact, that's what the, in fact, that's what the FETs are known as. They are known as voltage controlled resistors. And if you model the device when it's on as a resistor, it'll have a resistance as RDS. That will be the resistance of the channel, right? Current is not infinite. If current is not infinite, it has a fixed finite value. That means there is opposition to the flow of current, which can be modeled as a resistor. So if you model that as a resistor and you connect a output resistor to it, and you apply some sort of input voltage at the input, right? Let's say we design the device so that the resistance RDS is far less than RO. Well, RDS and RO form a voltage divider network. If RDS is very, very small compared to RO, then most of the voltage drop that is being applied will come across and be available across RO. So if RDS is far less than RO, then VO would be approximately equal to Vin. And it will have a linear relationship because we are operating the MOSFET in the triode or the linear region. And when we do that, we can refer to this as an analog switch. Okay, analog switch. And because it's allowing current to pass through, it's an analog gate, analog transmission gate. Okay, so single FET can be used as a analog transmission gate. The voltage that controls this switch is known as the controlling voltage, VC, that's applied to the gate. technical terms, it's simply VG, right? You apply voltage at the gate, simply turning it on. The voltage is chosen such that the transistor remains in the triode or the linear region, okay? It does not go out of the linear region. So it is on, but it's not in saturation. So analog switch. We can extend this concept further by combining two devices together. So a PMOS and an NMOS device. Here's the source connected together. Here's the drain connected together. And the input or the output can be taken at both ends. So V in is applied here. V out is taken here. There's a controlling voltage VC and VC bar. This is NMOS. This would be PMOS. VC is the controlling voltage. And VC bar would be the opposite of VC, right? Because it's PMOS and NMOS. If VC is positive and VC bar is negative, then both MOSFETs are on. And anything you apply at V in is available at V out. If VC is negative and VC bar is positive, then both are off. And to take it one step further, because we are using two opposite devices, we can use both terminals as inputs and both terminals as outputs. So this is a bidirectional transmission gate. Okay, hence the arrow pointing in both directions. If you look at the symbol of this transmission gate, it comprises of two arrowheads, and both of them are pointing in both directions, two opposite directions. Hence, bidirectional transmission gate. Okay. All right. Any questions? Okay. We'll end class here today. We'll pick up here again on Friday. We are almost at the end. We actually picked up the pace in the last week and earlier this week. So we'll wrap up by Monday or at least by half of Wednesday. Yes. Yes. I think there are